We're going to talk about section 2.3 in our books, piecewise functions. So a piecewise function is something that is given in pieces. So I'm going to come up with a function here, f of x, and we're going to say that it's going to look like x squared for x less than or equal to 2, and it's going to look like 6 minus x for x greater than 2. I'm having a hard time writing on my surface here. Okay, so first let's ask some questions before we try to graph it here. So suppose we want to know, can you find f of negative 2? Wait, I'm going to pause this. Okay, so we're going to try to find f of negative 2, and then we're also going to try to find f of positive 2, and what is f of 5. So in our piecewise function, we need to know, where does this x value negative 2 put us? So these are the parts that determine which branch of the function we're going to go to. So since negative 2 is less than or equal to 2, that's going to put us into the x squared part. And so that means we're going to take negative 2 squared, which is positive 4. So f of negative 2 is positive 4. We do not plug it into the 6 minus x part. Now the positive 2, again, because of the or equal to that we see here, it's going to go also into the squaring part of that function. And so it also is going to be 4. Now we still have a function because remember we have an input value of negative 2 that gets paired only with 4 and an input value of positive 2 that gets paired only with 4. So this is many to 1, but not the one to many that would make it not be a function. Now the 5, because it is greater than 2, it is going to have to go into the 6 minus x part. So we'll go 6 minus 5, which is 1. Now let's talk about graphing this thing. So I'm going to put an axis in here. And so the idea is that this is going to look like a parabola when x is less than or equal to 2. So we know that y equals x squared looks like a parabola that opens up and has vertex at 0, 0. But I'm not going to go forever to the right. I'm going to only go until we get x equals 2. Now when x is equal to 2, 2 squared is 4, so that means that this part of the parabola is going to come to an end at the point 2, 4. And because of the or equal to, that means that's going to be a solid dot as opposed to an open circle. So that part is the x squared part of the graph. Now I'm going to switch to the 6 minus x. So I know that's going to be a straight line, so y equals 6 minus x, but I don't think slope and y-intercept serves us as well here. Instead, we're going to think of plotting 2 points and then connecting those. The first point that we want to plug in is that boundary point 2. So when x is equal to 2, y is going to be 6 minus 2 is 4. Now that is a strict inequality, strictly greater than 2, so that would be an open circle. But it just happens to fall exactly where the solid dot was from the parabola, so that point will be shared by the 2 pieces of our graph. Now I'm just going to plot another point. I'm going to plug in 3. Anything that is greater than 2 will work. 6 minus 3 is 3, and so I'm going to go to the point 3, 3, connect that, and now I'm going to connect those two with a straight line, and so this is our piecewise function. It's going to look like that, and in this case, the 2 pieces actually connect, so we would call this a continuous function. So let's look at a new example of that. So let's say on this one, we're going to say that g of x is going to be the piecewise function, and let's say x plus 1 for x less than or equal to 2. Let's say it's going to be 1 for x equal to 2, and let's say it's going to be, we'll say 3 minus x for x greater than 2. So we're just going to graph this one and see what happens here. So again, we're going to have different pieces. This one has 3 different pieces. Now for the first part, for the y equals x plus 1, I'm going to plot the boundary point as one of the points. So I'm going to plug in x equals 2, and that's going to give us a y value of 3. So at 2, 3, because of the strict inequality, I'm going to put an open circle. Now this part of the graph, this part of the function x plus 1 is valid for all values of x that are less than 2. So I'm going to pick another number that is less than 2. I'm just going to plug in 1, and 1 plus 1 is 2. So that's going to make 1, 2 a point on the graph. I know this is a straight line, so I'm going to connect those two with a half line. That line is going to go over to the left. Now I'm going to switch to the middle part, which says that when x is 2, y is 1. So that means we're going to get a solid dot right there at the point 2, 1. So you're going to see that that dot misses that open circle, so there's going to be a break in the graph. Finally, I'm going to graph that third part, that y equals 3 minus x. I'm going to plug in the 2, that boundary point, and 3 minus 2 is 1. So on that part, the 2, 1 is going to be, did I do that right? Yeah, so the 2, 1 is going to be that exact same point. So the open circle, I didn't really put that first one in a very good place. Let me move it a little better. So there's the 0.21 we got from that middle part, and the second part is going to connect with that as well. So the open circle that we get from the second one will be filled in by that solid dot from the middle part. Now if I plug in any value of x that's bigger than 2, like say 3, 3 minus 3 is 0, so that's going to allow me to connect those points, and our graph is going to look something like that. Okay, I'm going to move to a new screen here. Now we're going to do a little different twist. We're going to look at a graph, and we're going to look at our graph, and we're going to write a piecewise function. So we're going to come up with the function. I'm going to give you the graph, and then we're going to come up with that equation of that function. So our graph is going to, this is going to be our axis, and I'm going to say that on this we're going to have 1, 2, 3 to the left, 1, 2, 3 down, 1, 2, 3, 4 to the right, and 2 up. So on here we're going to have an open circle at 0, 3. It's going to go through the point -3, 0, and this is going to be part of the graph there. Then it's going to jump up here and be a solid dot, and that's going to go horizontal until we get to a solid dot at 3, 2, and then we're going to rise 1 and run 1, so that's going to give you an idea of the slope there, and that's going to continue as a line forever. So we are going to say our function f of x is going to be in pieces. So looking at the first part there, we can see that our slope, since we go from this point, we're going to go down 3 and right 3. That's going to make the slope be a -1. We can see that its y-intercept wants to be a +3. So we're going to say it's going to be a -x plus 3. There's our y equals -x plus 3. And that's going to be for the y values that go from 0 to the left. So that's for x less than 0. Now I'm going to jump up to that middle part here. Now that's just a horizontal line at 2. So that part is going to be the line y equals 2. I wrote 3. So that's going to be y equals 2. So I'm going to say just 2. That's going to go from x values 0 to 3, and I'm going to include both of the endpoints. So I'm going to say 0 less than or equal to x less than or equal to 3. Then we're going to switch to that part of the graph that is going to go up. So that looks like it's going to rise 1 and run 1. So its slope is going to be 1. Now the y-intercept is going to be a little trickier. Let's see. If we have a slope of 1, I'm going to count over. So if we go over 1, down 1, over another 1, down another 1, over another 1, down another 1, means it's going to want to have a y-intercept of negative 1. So a slope of positive 1 and a y-intercept of negative 1 is going to make that part of the graph be a y equals positive x minus 1. So I'm going to say x minus 1, and that's going to go from this x value on. So that's going to be for x greater than 3. I could get away with x greater than or equal to 3 because that would be the same shared point there that we had before, but it's generally not a great practice to have these boundary points defined in two different places because we couldn't have them be different numbers or it wouldn't be a function. Let's try another one. So in this one, I'm going to give you a graph, and we're going to say we're going to go 1, 2, 3 to the left, 1, 2, 3 up, 1, 2, 3 to the right, and 1, 2 down. So on this graph, we're going to have an open circle at negative 1, 1. We're going to have a solid dot at negative 3, 1, and a straight line segment connecting those. Then we're going to jump up to negative 1, 3 and have a solid dot. And we're going to have another solid dot at 1, negative 1. And that's going to put us with another straight line segment that goes through there. And then we're going to have an open circle at 1, negative 2, and an open circle at 3, negative 2, and that's going to be a horizontal line segment there. So let's see if we can come up with a piecewise function for that. So looking at this first piece here, we can see that from counting rise over run, our slope is going to be, let's see, a rise 1, rise 2, run 2. So the slope is going to be 2 over 2 is just 1. Now the y-intercept, if I kept going over 1, up 1, that would give us a y-intercept of 2. So that part of the graph is going to look like y equals x plus 2. So I'll write x plus 2, and that's going to be for x values that are in between negative 3 and negative 1. So I'm going to go negative 3. I'm going to include that because of the solid dot, but not include the negative 1 because of the open circle. We're going to jump to the next piece over here. Now that looks like it has a slope of, I'm going to go down 2 over 1. So that looks like it has a slope of negative 2. And it looks like it has a y-intercept of positive 1. So that part is going to be y equals negative 2x plus 1. So I'll call that middle branch of our piecewise function. And that's going to go from an x value of positive 1 to an x value of negative 1 to a positive value to an x value of positive 1. Those are both solid dots, so we include both of the endpoints there. Finally, we get this horizontal line, and that's at a y value of negative 2. So that would be the graph of y equals negative 2. And the x's are going to go from a positive 1 to a positive 3. And the open circles mean that that's going to be strict inequalities. Okay, let's do another panel here. And we're going to now talk about an absolute value as a piecewise function. So absolute value as a piecewise, piecewise function. Okay, so we know that the graph of y equals absolute value of x looks like a V, and it has a vertex at the origin. You also know that the absolute value of x, if you plug in a positive number there, the absolute value does nothing. So we would say that the absolute value of x is just x whenever x is positive. Now, if we plug a negative into the absolute value of x, then we say the absolute value just makes it positive. But what that means mathematically is that the absolute value of x is the negative of x. So it multiplies that negative value by a -1 to make it be positive. As a result, our definition, the actual mathematical definition of absolute value of x, is that it is just what you see, the face value x, whenever x is greater than or equal to 0, but it's going to be the opposite of x whenever x is negative. So there is the piecewise definition of the absolute value of x. So let's see how this works. Let's try writing. We want to be able to write other absolute value expressions as piecewise functions. So let's write the absolute value of x minus 5 as a piecewise function. So what we want to know is, where does this stuff that's inside the absolute value, change from positive to negative? So we know that x minus 5 is equal to 0 when x is 5. So what that means, what that's saying, is that if we pick values of x that are bigger than 5, then the quantity x minus 5 will be positive. And that means that the absolute value will just leave it alone. So we'll just get the face value x minus 5 whenever x is greater than or equal to 5. When x is less than 5, then that x minus 5 value will end up being a negative, and so the absolute value will make it the opposite of that. It'll change it into a positive. And so you could either write it like this, or I'm going to go ahead and distribute it and say it's going to be negative x plus 5 whenever x is less than 5. Okay, let's do another example that's a little complicated. So let's write the absolute value of 2x minus 5. Let's write that as a piecewise function. So once again, what we're going to do is we are going to find out where the boundary is. Where does this change from positive to negative? And that's going to be at 5/2. So our absolute value of 2x minus 5 is going to be, now as long as x is greater than 5/2, 2x minus 5 will be bigger than 0, and so the absolute value will be just the face value. That is, it's going to be just whatever 2x minus 5 is. But when x is less than 5/2, the result is going to be a negative value, and the absolute value is going to change the sign of that to positive by multiplying it by -1. And so that is going to become a negative 2x plus 5 when x is less than 5. Okay, very good. Let's do another example. This is going to be a verbal example of a piecewise function. So we're going to say that a data plan data plan for a phone charges 99 cents per day, so 99 cents per day for data usage up to 20 megabytes. And 7 cents per day, or 7 cents, let's say, for each megabyte above that. 7 cents, one pen, for each megabyte above 20. So we're going to try to then see if we can write a piecewise function for the cost in terms, in terms of the megabyte usage that we will just shorten up and call M. And then after that, we're going to see if we can graph it. Okay, so what we're going to say is our f of x is going to be, so if we use less than or equal to 20 megabytes, I guess I should call those M's. And I guess I should call that an M too. I don't know if it'll allow me to change that. Let's call that, and let me call it, since we're talking about the cost, let's call it C of M. So when the megabyte usage is less than or equal to 20, then we're just going to pay that 99 cents. So I'm going to leave the cost in cents rather than writing that as a 0.99, although you could. Then that would just make that the cost is in dollars. Now, once we get above 20, then what we're going to do is this is where it gets a little tricky. We're still going to pay that 99 cents for the first 20 megabytes of usage. Then we're going to pay 7 cents for each megabyte above the 99. So I'm going to go M minus the 20. So this quantity is going to tell us how much above 20, and then for each of those above 20, we're going to multiply by 7. So there is our piecewise function. Now, to graph that, what I'm going to do is I'm going to call megabyte usage over here, and I'm going to call the cost over here. And I'm going to make our life easier, I'm going to call, there's 10 megabytes, there's 20, there's 30, and so on. And I'm going to just say this, I'm not going to be scaled great, but there's 99, and then I'll just imagine what it's going to go up from there. So our graph is going to be this, no matter if we use no megabytes at all, we don't use our phone at all, we're still going to pay that 99 cents, and we're going to keep paying 99 cents all the way till we get to 20. And if we stop at 20 megabytes, our cost is still going to be 99 cents. But then it's going to start going up with a slope of 7. So we're going to say it's going to then go up 7 after that. And so that is going to be the graph of our piecewise function. Okay, hopefully this will help you with homework number 11.